Due to the Paris Agreement in 2015 and the challenges of energy-climate nexus, energy system modeling, ESM, has acquired relevance and been used widely in energy planning, especially for energy security and the environmental sustainability, and above all, to set and assess plans for the energy transition. Today, ESM is widely used for supply and capacity planning, and above all, to provide an overall understanding for the whole energy system. For instance, they might be used for demand modeling, demand response management, and demand estimation for the future years. For example, if we take a typical energy system, we have an overview on all types of energy production technologies and the different sectors of demand, which are connected by the transmission lines. Since the energy supply needs to satisfy the energy demand, it comes to be of utmost relevance to have accurate representation of the demand side to design the supply system properly, estimating costs and evaluating the environmental impact. There is no unique classification for the different mathematical techniques and characteristics for energy demand modeling. However, we can highlight 3 points as the main characteristics, which can be used to differentiate the model used for a certain required application. First, in terms of the analytical approach, we have either top-down or bottom-up analysis. Secondly, the time-step resolution, varying from minute by minute, hourly, or on yearly basis. Finally, the simulation methodology, whether it is deterministic, stochastic, equilibrium, or optimization. Analytical approaches are often the first choice in modeling application. There are two primary methods for building a model: top-down and bottom-up. Top-down models are typically econometric models that link the gross domestic product, GDP, and the economy's added value to the energy used in different sectors. These models simulate demand to estimate its future evolution under various scenarios characterized by different input parameters. The main advantage is that they capture the overall economic perspective and link it to energy-intensive sector, which is useful for simulating different future scenarios and understanding their impact on the energy demand. The main drawback is that they require extensive data to precisely characterize each sector within a country or an economy, which often leads the modeler to make several assumptions to maintain the broader perspective, often at the cost of finer details. On the other hand, bottom-up models are built using an end-use method, starting from the appliance or the user levels and aggregating usages to categorize consumers and sectors. The main advantage of this technique is that it allows the modeler to understand real-life system interaction by simulating demand at various levels, either a household, a district, a municipality, or a region, which in turn provides a detailed view of energy consumption patterns from ground up. However, assembling detailed data from the bottom up can be complex and time-consuming. Additionally, the modeler may initially focus on local or specific sectors, which potentially could lead to miss a broader economic trend. The second important characteristic in modeling is the choice of time-step resolution, which can vary from minute by minute, hourly, to a year interval. Defining the appropriate time resolution is essential and should be based on the specific modeling application. The modeler must assess all available data, including historical data, for the load curve and also for the renewable resource availability throughout the day. The choice of time resolution should align with the targeted system requirements. When choosing the time-step resolution, oftenly the modeler has to check two factors. The first factor is data availability, as minute by minute, hourly. Models require more detailed data, which may not always be available. The second point, or the second constraint, would be the computing power. In order to have higher resolution models, minute by minute and hourly, they require and they demand more computational resources, significantly increasing the simulation time. The third point, or the third characteristic of the demand modeling, would be the choice of simulation methodology. Demand modeling is typically estimated using simulation rather than an optimization, due to the unpredictable nature and time variations of the energy uses. And this is influenced by various factors. However, the simulation methodology can vary between applications, and there are mainly two types of simulations. Deterministic simulation, and is used if the modeler already knows when and for how long an appliance will be used. A deterministic simulation can be employed in this approach. In this approach, the final demand is simply an aggregation or a sum of the appliance usage over daily, weekly, or annual periods. The second type of simulation methodology is stochastic simulation. If the modeler is uncertain about the exact usage times but has information on the probability of occurrence and a time frame where usage is most likely, a stochastic simulation can be used. This approach better reflects real-life variation and stochasticity, providing a more realistic simulation of energy demand. Let's consider the energy demand modeling for the railway sector in Italy, which encompasses three levels of demands: the railway station, the operation of the rails across Italy, the energy demand for train traction. Based on the modeling characteristics we have discussed before, what do you think would be the choice for each level of the demand modeling application? For example, let's take the railway station to apply our methodologies. First, the modeling approach, the choice would be bottom-up. And the reason why, that railway stations share similarities with residential sectors. Services within the stations, such as restaurants or bars, have appliances usage patterns akin to households, including the cooking, lighting, and air conditioning. These patterns vary throughout the day and depend on the number of people present. Second, the time step resolution, and the choice would be hourly in this case. An hourly resolution captures the daily fluctuations in the energy use, reflecting changes in appliance usage and occupancy levels. Third, the simulation methodology, the choice would be stochastic simulation. And the reason why is that while we know the service is available, we don't have precise information on the duration of appliance use or the number of customers at any given time. Stochastic simulation then would account for these uncertainties, providing a realistic reflection of real-life variability. In this lesson, we have seen the methodological roots for energy demand estimation. And in the following lesson, we will be introduced to a practical tool for these kinds of applications.